Okay, so
I'm going to talk about elastic braids, and not just general elastic braids, but elastic braids which make knots of particular type. I mean torus knots of N2, because they are made of braid, two braid. Okay, a little bit about motivation and historical development. So first, my first observation, probably it's not so new, that application to DNA is a strong impulse in the development of the elasticity theory. I mean the application of thin elastic rods, as first was suggested by Craig Manham and Lebre back in the 70s. But here I'm particularly interested in elastic braids. And so first simplistic models for DNA braids, or plectonyms, appeared back in the 80s, and they're very simple, just double helices, double helices. And then later, so people added some electrostatic potential to for interaction between individual strands, and after that there was a theory. The theory appeared which considered elastic plies made of two elastic strands, but with straight axis. This is important. And surprisingly, but we don't know much about the elastic braids with non-straight axis. There were some approximate approaches, and the most comprehensive theory that exists so far is so-called birod theory by Maher and Maddox. This is very general theory, but it's aimed basically to model a single DNA. So each strand in this birod is the single strand in the DNA. So birod means it's formed by two single strands which interact through hydrogen bonds. And so currently, our current project is to model two double-stranded DNAs which can interact to each other. That's the difference. So, but basically, the theory will be applicable to anything, to a structure like that. So I want to know the shape of this wire. A little bit about kinematics. So we have two central lines which are separated by the constant distance along the chord D1. And this induces a common parameterization for both curves. D1 is orthogonal to both tangents, and we can introduce two braid frames, so based on tangents and the chord vector, and correspondingly two material frames which differ from braid frames by phase angles, xi1 and xi2. Of course, each frame has its own orientation matrix, and so using the hat isomorphism, we can write four Darboux vectors or strains here. So the red one is important because it will be our working variable. So we have three angles, two sides, two phase angles, and one angle between tangents, eta. So we have a relation between matrices and correspondingly between axial vectors. And of course, it's easy to compute the contour length of the second central line as a function of the common parameter, which is taken as a arc length of the first strand. And we can compute the length of the second strand easily now. So that's all about kinematics. And now Why is it green? I have no idea. So we ascribe some elastic strain energy to each of the curves. Basically, we have two hyperelastic rods, and U is just the sum of this energy. And this is important. What we do, we switch from the individual strains to the strain of the first braid frame. But we have to pay for this because now the first derivative appears in the functional. There also could be interaction energy, which is assumed to be local. So this is for more general theory, and today I neglect it. So there is no interaction, only hardcore interaction between strands. And so we have this constraint at the end, which is constant vector, which is essentially force, and W is the work done by N force. So we can form now the action with this Lagrangian. Okay, so forget this. This is interaction energy, and this is a constraint on the second of the length of the second strand. And if we write it in the coordinate form, then we would have the second derivatives here of the orientation matrix. But okay, so and to find the solutions, to write the equations, we apply a Hamilton principle. So we're looking for stationary solutions of the action. But we want to write the equation in a reduced form. It means that we express everything, so our Lagrangian as a symmetry reduced Lagrangian in this form. So instead of coordinates, the Darboux vectors appear here, but it is second order Lagrangian. And now we can use the recently published, developed theory due to Gay Balmas and Trasser. So just applying this theory, we can obtain the equations, our equations, which are, well, equivalent to standard Euler-Lagrange equations, but written in the Euler-Poincare form. So these first two equations basically are balance equations for force and moment balance equations. We also have two standard Lagrange equations for phase variables. And so what's new now is that our moment is Euler operator for reduced Lagrangian. And it means that this is actually replaces the constitutive relations. So now we have constitutive relations which are differential. But still the whole system is, well, it's not quite ODE, but it's differential algebraic in any case. Okay, and now I specify so our potential or Lagrangian to the case of the two homogeneous and extensible isotropic rods. So with probably with two different bending stiffnesses and torsional stiffnesses. But okay, as I'm going to consider elastic rods, then of course these coefficients should be the same because we just have a one curve. Okay, and now I should formulate the boundary conditions. Okay, so I have the equations which describe a general two braid, and I want to close it in such a way that the end of the first strand matches the beginning of the second and vice versa in a natural way. So in order that two strands form just one curve, the one closed curve. These are boundary conditions. So Q's here are the quaternions that describe orientation of the first braid frame. So these boundary conditions guarantee the smooth closure of the two strands. So we have a system of equations, we have a boundary value problem, and next we need to know some analytic starting solution to start the parameter continuation, which in our case was performed by Otto. As one of the starting solutions, the velocity circles can be used. So this is geometric solution. There is no interaction between them. But formally, this link solution satisfies the equations. Another starting point is just two stacked rings. So first, so-called flat solutions. They are not quite flat, but they are twistless. So it means that we ignore the torsional stiffness now, and this is unknown. So two projections of the knot unknown. This is so the force here. The force is constant vector. The force here is orthogonal to the screen plane, and this arrow shows the force. And this is the contact pressure. So we have hard core interaction. We can compute contact pressure. It's rather complicated, but it's possible to do. So here you see that it's positive. Both it can be positive and negative. Negative means that they should be glued together. But this is only for the flat unknown. This is curvature. It shows that over the contact curve. It shows that the contact curve is not a circle.
This is a 1-2. It goes twice around?
Yes. Yes.
A 1-2 times.
Yes.
Not a 2 component.
So next, we can continue this series. This is trefoil, pentafoil, and so on. So the pressure grows, actually, which I think that's quite natural, and it's positive. So these are so-called flat solutions. These flat solutions, or twistless solutions, or no, twist is not quite correct. So this without torsional stiffness solutions, that they live on this bifurcation diagram on these V-shaped branches. So the plane here is the force, which is constant, the amplitude of the force against twist. So if we take one V-shaped branch, then we have right and left parts, and right is for over twisted, left for under twisted. For example,
what are the two axes on this plot?
Twist and force, as usual. So this is similar to what we have for single rod. So this is the pink V shape is for the trefoil, for example. And next is 7 foil, 11 foil, 15 foil. They are Carol, so this is for right-handed. And so the squares, black squares, show the first bifurcations, or the points where we believe they lose stability. And there are transitions branches which connect, for example, 3 foil to 7 foil. And this is how it happens. So we have 3 foil, then it deforms like figure 8, and then self-intersect, because so the theory doesn't describe the contact between the braids. And of linking number here changes by 2, of course, and after that it deforms back to the flat septafoil. So all the nodes are connected through these transition curves. So over twisted trefoil is connected to under twisted 7 foil. Over twisted 7 foil is connected to under twisted 11 foil, and so on. So difference is 4 because the linking number of trefoil is 1.5 and 7th foil is 3.5, right? So the same shapes, but with pressures. So you see that pressure could be negative.
The color coding of the pictures of the nuts is also showing that.
Yes. The color shows the pressure. Yes. Thank you. So another interesting thing. So this is how the different modes look like. So I just took 7th foil, septa foil, and show the. Oh, sorry, no, this is not about that. So this is a secondary mode for buckled septa foil, for under-twisted, for over-twisted. There is triple self-intersection, and it became cable trefoil. Here, if we move in this direction, and if we consider over-twisted trefoil, septafoil, sorry, so it becomes cable trefoil, but as you see, the different chirality, different headedness. And after that, actually, the curves find its way to the some another V-shaped curves, which are for multiple colored, flat in Quantised solutions, but they are heavily overlapped, so they have no physical meaning. So we haven't computed them. So the same shapes with pressures. Okay, and here, so this is first 3 modes of buckled 11 foil. This is first mode, figure 8. This is 2 second mode. This is third mode with pressures. So that was right-hand side of the bifurcation diagram for positive twist. So for negative twist, we have correspondingly pentafoil and so on. But now they have different headedness, because so right-handed trefoil is connected to left-handed unknot, and the left-handed unknot is connected to a left-handed pentafoil, and so on. The same story, but in opposite direction. So basically, the whole structure can be described. It's separated, so in 2 classes. One of them may be obtained from right-handed trefoil, and the second one from left-handed trefoil. The most interesting things, so this is, okay, so it's even more complicated, because the transition curves actually, they're pairs of transition curves depending on geometry. And for example, here and here, sometimes they coincide, sometimes not. So you see that the shapes differ because of, it depends on the commensurability of the mode and number of the mode and given knot type. Okay, this is the last. This is central part. It's more complicated actually. The transition between unknot and trefoil is rather complicated. I think I should stop here.
I suggest that as Simon sets up, that we take questions, and also there'll be some time at lunch for more. So there's time for a couple questions. Quick ones. During the talk.
Maybe I have a curiosity. Is just a technical point that doesn't affect your. I just wrote a paper 15 years ago on supercoiling of elastic strings. I remember from then that I could get rid of the tricky boundary condition requirements by using linking number. The input came from topology. You have closed curves here. Yes. And so the twist, the torsion, you can relate the torsional energy to the difference between link and writhe in terms of twist.
Well, we can compute it.
Yeah, no, you can compute it, but I wonder if you can use the conservation of linking number to avoid boundary conditions. I wonder if you can do that. I remember that.
Technically, well, probably for some analytical purpose, some approximate shapes, yes, but technically for numerically,
Mhm.
I think it's I don't know how to do this because
Yeah, but it would be easy. It would be easy. It would be probably simplify your, I don't know. Well, okay.
we can discuss it.
Okay.
Okay, thank you.
No other questions? If not, let's thank Eugene again.